seminar this week. And it's our great pleasure to have Professor Jeremias Sulam from Johns Hopkins to visit us and give the talk. And I think many of you here may be already familiar with Jerry. And he currently assists professor in BME at Johns Hopkins, and he also affiliated with Mathematical Institute of Data Science and Center for Imaging Science, GTU. He graduated from Israel, Technion in 2018, and with Mickey Lab, which is very famous in sparse representation in learning. And his major research interest is in machine learning, sparse representation, solving inverse problem, etc. And he received a couple of awards. That's a career award at the award from Argentina engineering or something I forgot.
Oh, the National Academy of Engineering.
National Academy.
I didn't know you were trying to say.
My fault.
Yeah, that's fine.
Without further ado, let's welcome Jerry for his interesting work on what's in my network. I learned proximals and testing for conditions.
All right.
Welcome.
Thank you. All right. Good afternoon. And thank you for having me here. And thanks, Ching, for the very kind invitation and for very kindly hosting. So also for all of, everybody who's here, I should also say thank you for picking this talk instead of Mickey Lustig's talk, which is happening in another building, but I'm hoping that you won't be disappointed. Okay, so I'm going to tell you a little bit about ways in which we've been trying to think together with my students on how to frame questions of interpretability. Now, to begin with, what we are going to do first is look at this bit of a beta lesson. This is a blog post written by Rich Sutton, very much in the spirit of Halloween. And so let me just read it out for you. So Rich Sutton writes, the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. Seeking an improvement that makes a difference in the shorter term, researchers sometimes seek to leverage their human knowledge of the domain, but the only thing that matters in the long run is leveraging computation. We want AI agents that can discover like we can, not AI agents that contain things that we have already discovered. So this is basically called the beta lesson because indeed, many people, including most of the people in this room, I presume, we often take a lot of pride in understanding a lot of knowledge about a domain, a very specific domain, and then using that to come up with better learning algorithms. And Rich Sutton here is apparently saying, well, actually, there's no need for that as long as you can scale up computation and data. So I would happily push against this. I don't think this is quite correct. But what is sort of inevitably and very hard to argue against is that we are having increasingly algorithms that learn from data and come up with with solutions to very hard problems that we have a hard time understanding how is it that these algorithms have come up with these solutions. And there is a limited understanding that we can gain from these problems that we wanted to solve in the first place. And this is not just an intellectual problem, it's also a problem from a regulatory standpoint, I would argue. So I'm curious, by the way, who has seen this notice, this presidential order? So some of you. So last year there was this presidential order from the White House, which is basically a set of guidelines, sort of instructing the public and everybody on how we should start thinking about potential regulations and guardrails on deploying AI tools in the wild. And there's a big stress here in terms of trying to understand the complexity and opacity of these models. So my research theme sort of aligns very well with this mission. And what I hope to tell you today is two ways of looking at this problem. One of them is going to be in the context of inverse problems, which is something that's very close to my heart. And then we are going to look at a very different work on how to ask questions in terms of in supervised learning problems in image classification. Okay, let's begin with inverse problems. And I assume most people in this room are already familiar with inverse problems. These are settings where we are trying to estimate an underlying vector. We are going to use images in general that have undergone some degradation process. So you could think of trying to estimate, for example, the ground truth photograph from an old degraded one, or you could try to estimate, for example, a super resolved microscopy image from a low resolution one, or doing MRI reconstruction. Or maybe you went on vacation with your partner and then you split up and then you want to remove that partner from your picture and you want to inpaint whatever was behind your partner. So in general, and a little bit more formally, we are going to restrict ourselves for the most part to linear inverse problems. We're going to assume that we have an operator A that we know, and we get measurements Y up to some noise B. And of course, the goal is to try to estimate X. And one very popular way of doing this is by solving an optimization problem of this form, where you are searching for X's that match your measurements, something that is likely under your measurement model. But of course, if you were just minimizing this is ill post. So there's an infinite number of solutions that can minimize this to 0 in general. And so we might enforce some regularization term. Now, this regularization term really is something that should tell us what is likely and what is not likely in our world, in our data distribution. And just to make that slightly more precise, you can take this and basically derive from it by using Bayes' rule, the fact that this optimizer is doing nothing else than trying to estimate a map, the maximum of the posterior of your unknown given your measurements. And what I want to stress is that this is true as long as you have a regularizer that is basically minus log P of X. It should be inversely, it should be minus the log density of your data. Okay, keep this in mind because it's going to be useful in a couple of slides. So what do we need in order to solve inverse problems? Well, we know we need some good regularizer. And of course, we don't know P of X, so we need to come up with some regularizer. So how have people been designing regularizers? Well, if you go back 100 years or so, someone would say, well, you know, a regularizer might be a low L2 norm, because maybe the L2 norm distinguishes between pure Gaussian noise, which has a lot of energy, versus natural images would perhaps have less energy. That's kind of rough. That's not going to do too good of a job. Maybe you want to introduce a linear operator, and so you ask for smoothness. And maybe the L2 is also not a great choice. Maybe you want to change the L2 for an L1 and maybe put a gradient operator here. So you're going to ask for things that are piecewise smooth or piecewise constant. Maybe you want to generalize that operator to for something like a wavelet frame and ask for sparsity of those wavelet coefficients. Or maybe you want to generalize this even further and ask for sparse representations, and there's some overcomplete dictionary, and you can maybe go and train this dictionary from data. And this is not just a unidimensional story. There are many other models that people have used, using a lot of ingenuity and sort of trying to learn something about a domain to try to tell us what are good regularizers to use. And then right around the time when Tao and myself were at the Technion doing our PhDs, deep learning came along. And deep learning was great because in some sense, it allowed us to solve a lot of these very hard inverse problems that we were trying to solve before much better and oftentimes more efficiently, at least at inference time. But the downside of it is that it got us to be a lot more lazy, in that now we didn't have to think hard about models of the world that would allow for efficient regularizers for our inverse problems. Seemingly, all we had to do was just collect a bunch of data, and somehow these functions would be able to learn something about the world that would enable them to come up with good solutions. So what I'm going to try to do now in the first 20 minutes or so is convince you that there are ways of getting something out of both ways of looking at this problem. Okay, so how have people been using deep learning in the context of inverse problems? Well, perhaps the basic thing that you could do, which is what people started doing a while back, is to say, well, I'm going to collect a bunch of pairs of ground truth xi and measurements yi, and pick a network. And when I say a network, pick a family of functions parameterized with parameters theta, and then just, if you have enough data, just train your functions so that if I give you corrupted inputs y, you can produce for me the x that would correspond to those y. And of course, if you know the forward operator, then you can use it to get something better. this is all good and simple. And people have been doing this for a long time. And this kind of works. It's not super stable. There are some issues with this. So maybe a slightly more principled thing that you can do is say, no, I don't want to move away from my variational perspective. I still want to solve an optimization problem. But now what I want is I want this regularizer to be learned from data and maybe parameterized by a network somehow. So how should you train this regularizer? Well, there is a whole variety of alternatives now. One thing you could do is remember what the goal of the regularizer was. We wanted this regularizer to distinguish things that are likelier under our data distribution and things that are not likely. So I can literally train a critic or a network that does exactly this. I can find a function R so that whenever I feed it X from P of X, R of X is very small. And when I feed it X from some alternative distribution Q, the regularizer is very high. So this is kind of like really asking a network to do this. You can do many other things. You can use generative models, like the group of Dimakis has done, or many other things like regularization by denoising and many other variants. In all of these cases, you should keep in mind that even though we are learning data-driven regularizers, and we can go back here and solve this optimization problem, we haven't really learned much about what is it that these functions are capturing about our data distribution that is enabling us to solve these problems. We end up with a neural network or a function that computes the value of these things, but we have little understanding as to what that value actually means. There's a question, yep.
Yeah, it seems to me that maybe the bigger issue with option A is that it assumes that there's like a bijective, like one-to-one mapping between the state X and the output Y, but if you have randomness in this process, then it's not going to be necessarily a one-to-one map. Or you can have an input mapping to a distribution of ones.
Okay, that's a good question. It's not quite that though. So remember, what I began with is saying that we want to estimate a map. So regardless, if you have a many-to-one map, I'm still trying to estimate a sample X that maximizes my posterior distribution. Okay. So in all of these schemes, I'm never trying to estimate a whole distribution. I'm never trying to sample. All I'm trying to do is just recover an unknown that maximizes my posterior. Okay. Okay, there's a third family of methods that I call implicit priors. And they're perhaps better motivated by the following. Let's assume that I knew my regularizer for a moment, R. If I knew my regularizer, then a reasonable thing to do, if you don't want to assume that R is smooth, for example, is to just run proximal gradient descent, which iterates between a gradient step of your smooth part and the proximal operator of your regularizer R. And the proximal operator of a function R is this function, is this operator, and it is the minimizer of a baby optimization problem. I call it a baby optimization problem because if you notice, it's almost the same as the original one that we wanted to solve, except there's no forward operator A. It's just as if here there was an identity matrix. Yeah. So the nice thing about this is that for a very large, well, for interesting functions R, sometimes computing this is very easy. And one thing to really note here is, as I said, if this problem is a simplified version of this problem is also solving an inverse problem. If I assume that U is just X plus noise, this thing is nothing else than a denoiser. And in particular, is nothing else than a map denoiser. It's estimating the maximum of my posterior of X given Y in a denoising setting. Okay, there's nothing new here, but about 10 years ago, people said, if proximal operators are denoisers, well, there's a whole industry of coming up with better and better denoisers. So then I'm going to just replace my proximal operator for a function that I don't know with a denoiser. And you can go to GitHub and plug any state-of-the-art denoiser. And in general, the better the denoiser, the better the solution that you will have for your original inverse problem that you what that you wanted to solve to begin with. And this has been very, very successful. It's very much related to enroll optimization and many other things. And it's a very, very active line of research. Now, the kind of elephant in the room here is, well, if I pick any neural network that is, or any diffusion model that's acting as a denoiser, when will I know that that's actually computing a proximal operator? And even if it were, for what regularizer? Okay, so that's exactly what we're going to answer now. So the first question is, I just want to understand if I have a function, perhaps a parametric function, when will this compute exactly a proximal operator? And for what function, R? So the way to think about this is I have all my functions from Rn to Rn, and I want to understand which subset of these are proximal operators for some other function R. Now, once we understand this, I don't care about any function in this set. I care about proximals for my log P of x, right? If I could choose, someone gave me the option, this is exactly the regularizer that I would choose, because I know that in the context of my Bayesian map estimator, this is the regularizer that I need. Okay. So let's answer question one, which turns out in hindsight is actually not too hard, because there's this very nice paper by Remy Grivenbal and Mila Nikolova from a couple of years ago. And this is a simplification of the results. But in a nutshell, what they show is the following. Any function f will be a prox of a function r if and only if there exists a convex function psi so that f is its gradient. Now, this function psi doesn't need to be smooth, and so this is a subdifferential. But the picture that you should keep in mind is exactly this. We care about f, and we care about f that is a prox for some r. And it turns out that this is true if and only if f is also the gradient of a convex function psi. And the cool thing about this is that r need not be convex. And that's why you see this inclusion operator here, because now if r is no longer convex, this minimizer may not be unique anymore. So in light of this, it's now kind of clear what we need to do. Just pick a function that is convex and differentiable. I'm going to call it psi of theta. It's going to be parameterized by a network. And then take its gradient map. And by construction, that function will be a proximal operator, always.
Yeah, if R is not convex, right?
Yeah.
The prox mapping this problem will be not convex, right?
Correct.
Yes, and then it may have a local minimizer relative to global. So the FX
Sure.
here denotes the global minimizer, right?
Yes, what this is saying is if I have a way of evaluating f of x, the point that you get will be in the solution set of that non-convex optimization problem.
Yes, so that means this global solution set must be convex.
No.
Not because phi x is convex now.
Mhm.
Then it's subgradient fx belongs to O. Maybe a subset, right? Fx belongs to.
Of what? It belongs to it.
I mean, fx is a global solution, belongs to a global solution
Yes.
set of
Yes.
prox mapping, and fx also belongs to a subset of belongs to a set of that subgradient. These two may have some relations.
Oh yeah, there's a very specific relationship between these three things that I'm not telling you. Yes, of course, of course.
Okay.
In fact, you'll see this relationship in a minute. Okay, so the only thing we need is a way of parameterizing convex functions. Turns out there's already quite a bit of literature for this. We use something called input convex neural networks. These are in fact universal approximators for convex functions. And so just pick a function in this functional class, take its gradient, the result will always be a prox. Okay. Now, great, it's going to be a prox, but for what function R? And R is important because it's the regularizer that we need. Turns out that, like you were hinting, there is an expression that relates all three things: the regularizer, my prox, and my convex function psi. And it doesn't matter that you remember this expression. It's a little bit convoluted. It's fine. The only thing that I want you to take away from this is that you can compute the value of the regularizer if you can invert this prox map, which sounds complicated, particularly because this prox is implemented by a neural network now. And so doing this kind of looks scary. Turns out it's not scary at all. And it just boils down to solving a convex optimization problem. So we can do this with conjugate gradients for like a normal sized network. So the bottom line is, if you give me a prox operator, I can give you the value of R of X. I can tell you, I can query what the corresponding regularizer is. And I'll show you examples of this in a moment, so don't worry. Okay. The perhaps more interesting question is the second one, which is, okay, fine. Now that we've understood what class of functions parameterize proximal operators, now I want my proximal operator to be the one that I need for my inverse problem. So I want my regularizer to be minus log P of X. But we don't know P of X. So we are going to try to learn it from data. So what we're going to do is draw X from P of X, and I'm going to add Gaussian noise to it. So I'm going to have Gaussian noisy versions of my X that are Y. And I'm just going to take a learning problem. I'm just going to say, hey, search for a function f in the class of functions that are proximal operators. Now we know how to do this. And minimize an expected loss of how well f of y can recover x. This is just training a denoiser, nothing else. Okay, so if we're training a denoiser, then the only thing that we need to do is pick a loss function. And so very quickly, like probably everybody would say, pick an L2 loss. So if you pick an L2 loss, that's actually the incorrect choice, because the L2 its minimizer will converge to the MMSE. And the MMSE is a conditional mean. So it's computing the mean of this posterior distribution. But that's not what we need. We need the maximum of that posterior. So you can switch to an L1 if you want, but that's going to converge to the median in high dimensions kind of thing. So the question is, what should this loss function be for me to converge to the mode of that conditional distribution? Who said 0, 1? Okay, great. Perfect. Okay, so here's the slightly more refined version of Jeff's answer. So there's a family of loss functions. This is just one example of them. It's just one minus a Gaussian, okay? And the argument of the Gaussian is the L2 error between f of y and x. And this Gaussian that you see here is controlled by this gamma parameter, standard deviation, sigma. All right. So take your function as the argmin of this limiting process, where gamma goes to 0. So this Gaussian converges to an L0 of this proximal matching loss. In the limit, that f hat will do what you wanted it to do. It will compute the mode of the conditional, which in this case coincides with the prox of minus log P of X. Scaled by sigma, and sigma is basically the noise that you use to train this denoiser. Yeah.
So the log probability to me looks a little bit like an energy-based model.
Yeah.
So I'm wondering if you use that, which is unnormalized, will that still work?
Perfect. Yes. So excellent. Let me move two more slides, and I think you. Perfect. Okay. So the first time we kind of started seeing these results, again, we would probably do what anyone in this room would do, which is say, okay, let me just draw data from a Laplacian, and let's see what happens. Okay, so I'm going to draw X from a Laplace distribution, 0, 1. Its log, it's the absolute value. And the prox of the absolute value of the L1 norm is just the shrinkage function, right? So here we know exactly what log P of X is, and we know exactly what the prox should be. So what we're going to do is just train a denoiser on this data Y. But that's it. The network or the loss function, it never knows that the data is coming from a Laplacian, right? So it's just training a denoiser. Okay. So in dotted line, you see the soft thresholding function. In blue and red, you have two proximal operators. These are proximal operators by construction, but these are proximal operators that are trained using an L2 and an L1 loss. And these are proximals, but they are the wrong proximals in some sense, right? So it isn't until you switch to these proximal matching laws and you make gamma go to 0 that you really start approximating the correct prox, which is the shrinkage. And now to your question, I can recover the primitive of the prox and give you this unnormalized version of P of X. Because I can compute R of X based on the prox by solving this convex optimization problem. And again, only if you use these proximal matching laws, you recover the correct unnormalized P of X. Yeah.
Probably have to use graduated non-convexity here, otherwise you probably have a vanishing gradient.
Yeah, exactly.
Second question, since if I recall, the function f is a gradient of something, and now you need to optimize again. You end up with sort of double gradients that have to be done.
Yes, correct. And in fact, for that reason, when I said that we use input convex neural networks, we use functions. So these input convex neural networks have some constraints so that you can only approximate and generate convex functions. Additionally, we use smooth activations because of this, because of the second order information that we have. Very good. Okay, fine. This works on 1D data, fine. Let's look at something slightly more interesting. I'm going to train this as a denoiser for digits. And I promise I'll show you something more interesting than digits in a minute. But so I train a denoiser for digits, and the value of the regularizer is very important, right? So I can now go and say, okay, I'm going to feed this nice looking 6 to a network, and I'm going to compute the value of the regularizer. And I get this value 2.23, which in absolute values doesn't mean anything. But then I can feed digits of increasing amount of noise, and then the regularizer shoots up, because indeed, these things are not likely under my data distribution. Okay, fine. Here's perhaps a slightly more interesting case. I'm going to pick a nice looking 4 and a nice looking 1. And for both of these cases, the value of the regularizer is quite small, right? Because both of these are likely under my data distribution. Now I'm going to take a convex combination of these two things. And these things in the middle are not a digit, right? And indeed, the prior shoots up for these middle points. And this is important because this would have not happened had we restricted ourselves to using convex regularizers. We are only able to capture this non-concavity of the density because we're using this framework. So you can do many more things. You can say, oh, let me just look at how this regularizer actually looks like. Here I'm just plotting a projection on 2 dimensions, but you can see that, oh, well, let me look somewhere, and you have these local minima where you have these nice looking digits. And then if you start deviating from them where the regularizer grows, indeed, the digit just changes, indicating the log likelihood drops. Of course, I'm showing you this on digits because it's easier to understand these things, but the same is true in more complicated distributions. So for example, here is a case for CT. So we train a model to denoise CT images. And as a denoiser, it's fine, it works well. But the cool thing is that now I can say, this is the ground truth. I'm just normalizing everything so that the regularizer here achieves a value of 0. It doesn't mean anything. But then I'm going to try to reconstruct this by using just 100 angles, 100 orientations. And instead of 100, then 60, and then 30. And you can see that of course, the tougher the inverse problem, the more artifacts you get. And that's exactly indicated by the regularizer. So this regularizer is doing what we wanted it to do, which is to capture what is likely under our distribution and what is not, but it's doing it only by looking at data that comes from P of X. Yeah.
So to me, this sort of feels a little bit like guidance and diffusion models, but it's on the training end instead of the inference end. So I'm wondering like what, I don't know, what's like the benefit of this versus doing something like that?
So first, there's no diffusion here whatsoever, right?
Right. Even it's the same sort of principle. You're using a pre-trained model for, or you're estimating the density of the marginal or of the unconditional distribution, and then you're using that to regularize your training of the conditional.
A little bit. It's again, it's not quite the same. So for example, in diffusion models, what you're trying to estimate is the score.
Right.
Here, which is a gradient of log P of X. Here, what we are doing is estimating the proximal of minus log P of X.
Right.
So it's a different quantity of this density.
Right, it's a different approach, but it's this, to me, it feels like the same idea. You're using the.
Philosophically, it's not correct. So philosophically, we're trying to learn something about P of X that allows us to solve inverse problems. Yes.
Right.
In particular, we want to do this through these sort of plug and play approaches as opposed to running diffusion processes. Also, another important difference is, in general, diffusion models, you estimate the score because you want to sample from this posterior. Here, I'm not sampling whatsoever. I'm just estimating a map, right? I'm just estimating the maximum of this posterior.
Okay, I see. Thank you.
But there are even further, more interesting connections too that I'm happy to talk more about offline.
Thank you.
Okay, now, Tao here cares a lot about convergence of these plug and play stuff. So remember, we wanted a denoiser, sort of a general purpose tool that we can plug here and obtain a solution to this general inverse problem. You give me a new inverse problem, a new operator A, I can still run this and get something. So because the prox that we are having, the network that we are training is computing an exact proximal operator, there's a lot of structure in these things that I can use to derive convergence guarantees. And so you can now use a lot of the literature on convergence of first order methods in non-convex settings, because again, now this R is not going to be convex. And so, basically here the analysis is convergence to a fixed point, but you can show that this type of proximal gradient or half quadratic splitting strategies or things like ADMM converge to a fixed point. So at least you know that you'll converge. And again, the goal was to have a general purpose sort of generic tool for general inverse problems. So here are some examples for denoising and deblurring. So here, maybe in the screen, you can't appreciate too much, but these images are blurred and noisy. And these are different estimates from different plug and play approaches. And basically the conclusion is that these methods, which is ours, based on these learned proximal operators, basically work as good, sometimes better, sometimes worse than all of the other plug and play stuff. But you understand exactly what these functions are computing. They're computing proximal operators. You can invert them and compute the regularizer that has been learned implicitly by these things, and also have as a byproduct convergence guarantees. You can also apply it to sparse UCT and compressed sensing, and even, I mean, there the results are even better. So these things work quite nicely. Okay. So far for inverse problems. Yes, please,
So
please.
to make those plots where you label the regularization value, you actually have to solve an inverse problem, an optimization problem.
Yes.
And that's a non-convex optimization problem.
No, that's a convex one.
Oh, it is. Okay.
That's
Because I thought, because it's a convex network.
Yes.
Yes. Okay. All right. So how expensive, how hard is that?
A second.
Easier to
Yeah,
train.
it's super. Yeah.
You're only updating the input, not the weights of the network.
Yeah. Exactly. Very good.
If you have an estimate of R, you can get the probability,
Yes,
like sample from.
yeah, you can.
Okay.
And that's very much related to the question that whoever sitting next to you asked before. Exactly. So this is really learning some quantity about a density, just like you would in diffusion models. These objects are different though. These are proximal operators instead of gradients of log probabilities. But yes, there are ways of sampling with this too that I'm not presenting here. All right, very cool.
Biomedical.
Yep.
I mean, just like a random question. So
Yep.
I think there's some work by Yueqi and other folks that running this diffusion as like a denoising for several steps as a regulator. Whether there's some relationship.
Maybe.
It's just open question. Maybe we can talk about this.
Yeah, maybe. I mean, here, remember, all we're doing is just taking a proximal step towards your density, right? So that's what this proxy is doing. And it's a one-shot thing. There's no diffusion process here. But yeah, maybe we can chat more offline.
It also depends how we use diffusion model. So there are different balance of way how to use diffusion model for user problem. So one possibility is something looks like a plug and play, but in other way, so it's very similar to this. That's why I guess.
Yes.
Okay. So we're going to switch gears to something very different. So if you got lost at any point, you can now try to catch up. This is completely independent from the past. But philosophically, we're trying to do the same. We have now a function that instead of computing, an output from Rn to Rn, we now have a predictor that gives us a label. You can think of multi-class settings, classification settings, where given an image, you have different scores for different classes. And this is, for example, an image of my cat. And I have a predictor that's a black box. And I would like to understand what features are important for this function to make this prediction. And so when I ask this question, kind of like inevitably a question that I need to ask immediately is, what do I mean by importance? Importance in what sense? And moreover, maybe the features that I care about are things that are very hard to quantify in the input space. So for example, maybe I care about asking questions of the form, is the piano important for this output, right? Or maybe that's too weak, and maybe I want to say, well, maybe is the piano important for the prediction being a cat, given that I already observe a cute mammal in the picture? And all of these things are very sort of abstract concepts that are not immediately clear how to map them directly to my input pixel space, right? So this is what we are going to try to do. And I should also stress that there are basically two ways of addressing this problem. One of them is to just try to build a predictor that is interpretable by construction. So that by construction, you can query your predictor in this sense. An alternative route is to say, well, no, I want to be able to deal with off-the-shelf predictors that someone spent millions of dollars training, and then I want to inquire these type of images, for example, for auditing purposes or debugging purposes or things of that nature. So that's what we are going to do here. Okay, so we need to get a hold of something, and that something is going to be some embedded space. So what I mean by this is we're going to have this is our predictor, it's fixed, and we're going to have an encoder, and from this encoder, we are going to obtain some features, H. These features are then classified by a classifier and giving us the logits that you see here for this prediction. So the trick is going to be able to capture some semantic information in this latent space, in this embedded space. So we're going to have embeddings H, which are a function of X. And we are going to have a concept band, which is just a dictionary of vectors in this embedded space. And each vector is going to have information about each of these semantic concepts. And this will become a lot clearer now in a minute. But imagine if you did have these vectors, then a way of computing these semantic notions is to just take inner products of this concept bank with your features H. Okay. My pointer just died. It's okay. So the question is, how can you construct these concept banks? So it's actually not, well, it's a bit easier than what one might expect. So for example, if someone gave you a data set of things that have things that are cute and things that are not cute, well, then you can push all these data through your encoder and then train a linear predictor in this embedded space, let's say a linear classifier, to predict things that are cute, things that are not cute. Perfect. This little vector of this normal hyperplane is now one of these vectors in my concept bank. Now, this requires you collecting a lot of data to train these things, and that's kind of cumbersome. That's okay. We now have better things. You can use vision language models where if you haven't seen this before, the nice thing about these models is that you have one model that has two different encoders, an image encoder and a text encoder, and they have been trained in such a way that they've been trained on pairs of images and text captions, so that once you push them to the same space, these two things have a very high correlation. So now, turns out these models that are sort of made available to us by OpenAI and other people, allow us to just push through this text encoder whatever concept we want, and we can compute these in our products and have access to these concept banks. So how do these concepts look like? Well, let's say that I compute these features, embedded features from this input image, and then I compute the inner product with a bunch of concepts, and then you get these things. You know, the highest correlation is with a concept of the word spaniel because it's close to a type of dog. Flu is also important because the dog is jumping, and some of them are kind of related, some are not related. You see the same with church, you see exterior or cathedral, which kind of makes sense. So, you know, you get some kind of notion of concepts that might be correlated with these inputs. But we want to understand these things a little bit better. So one thing you can do, and this is sort of has been the overarching approach to answer this question, is to say, well, if I have access to the semantic concepts, what I can do is train a linear classifier, W, on my semantics, Z. And so this predictor by construction is interpretable because it's a linear combination of concepts. And so I can interpret this very clearly. That's fine. The problem, though, is that first, you need a very large concept bank for this predictor to do a good job in predicting the label. And second, this kind of defeats the purpose of inquiring things about the original predictor that we wanted to study, because you end up training a different predictor. And of course, this y tilde might be very different statistically than y hat. And we care about understanding y hat. Yes?
So can I ask, like, what's the difference between this kind of inner product with the clip model? So like clip, they're also like aligning text, but like long prompts, multiple tokens with the image embeddings.
Yes.
So like you're doing a more fine-grained version of clip.
Yeah, but we're using clip too. You can use clip in this way too.
Yeah. Okay. So so maybe your text encoder and the image encoder is not like jointly trained, but you're just trying to.
Oh, we don't train it. We literally use clip.
Yeah.
So-
Okay.
So I guess what you're doing is you're taking clip and you're finding like basis vectors that represent text and then training a linear classifier.
No. I haven't told you what I do yet. Everything I've told you is how people frame this problem.
Okay.
And these what you just said is true about these, it's called concept bottleneck models, where, correct, you construct a bunch of concepts in this embedded space, and then you train a linear classifier on them. And then you try to, and then you can make claims about this. That's not what we want to do. We want to make claims about y hat. Okay. So this is kind of what we really want to do. We want to wrap something around this model so that we can give you a list of concepts according to some notion of importance. We want this to hold for any fixed predictor that someone give me. We want local and global notions of importance. I'm going to define what these are in a minute. We want to be as independent as possible of whatever concept bank you want to test for. I don't want to have to rely on having a very large concept bank. If you want to test for a couple of concepts, I want to be able to test for that. And I want to frame the problem in such a way that I can draw very specific statistical guarantees about my claims. So if I'm telling you that these things are important up there, I want the ones that I'm telling you that are important to satisfy, for example, type 1 error control or false discovery error guarantees, right? Okay, so what we're going to do is the following. Here's a notion of global importance. I can pose this notion, this concept of importance, this notion of importance as a hypothesis testing problem. So I can say, look, under my null, the J feature is not important. And what does that mean? It means that my response is independent of the concept J. That's a reasonable enough thing. And then if I were to be able to test for this and I were to reject it, I would conclude that concept J is important according to this notion of importance. That's kind of weak. And so this is something that's perhaps a bit better. You can say, well, is my concept J important in the sense that is it independent of my response given all the other concepts? All of these notions are global notions because they're looking at quantities that depend on the joint of Y and Z. What I want, though, is to instantiate this at a local level. So if I give you this one image of my cat, I want to ask questions about this cat in particular, not about things over the population. So let me skip that. So the way to frame this is in this way. Notation gets a little bit hairier, but I promise that conceptually it's very simple. What this is saying is that, remember, H are my features. What I'm asking is, I have features, and I'm sampling features conditioned on having observed concepts S and concept J. And this induces a response in my predictor. Is that distribution the same as the one induced by only conditioning on the concepts S? If these two things differ, I'm going to reject this null, and I'm going to conclude that concept J is important with respect to concept S. Here's perhaps an illustration, which is a real example that might convey the message better. Here there's an image, and the two labels gas pump. So what I want to understand is I want to look at the distribution of the logit of Y gas pump. Okay. What I'm going to do is condition on a random subset of concepts. For example, old, number, some things. And then I'm going to look at the distribution of my responses of Y hat. And I get a curve like this. Now I'm going to, instead of conditioning just on those random concepts, I'm going to condition on that and conditioning on the concept of Z dispenser. And it turns out that if you look at this distribution, it shifts to the right because now it's more likely for this to be a gas pump. And this is exactly our definition of importance. These distributions are changing, and so I will conclude that the concept dispenser is important for this prediction with respect to subset S. Now, if you do the same with a concept that is not important, you fail to reject. So if you do the same thing, but now you condition on the concept trumpet, which has nothing to do with this, then these distributions are virtually the same. I fail to reject, ergo, they're not important. So I'm running out of time. So unfortunately, I can't tell you very much on how we actually do these things. The 1 minute summary of this is that all of these notions of importance that I've been presenting can be formulated as two sample tests. I'm basically trying to understand whether samples coming from two distributions come from the same distribution or not. And there are traditional ways of testing for these null hypotheses. For example, you could collect data, compute p-values, and then reject or fail to reject. Or you can use sort of more modern approaches that rely on e-values and based on online testing procedures, where what we're going to do is monitor an e-value that's going to measure essentially a notion of evidence of an alternative. And then if this evidence is large enough, we are going to reject, and that rejection will have a type 1 error control guarantee. So I'm just going to sweep through this procedure of online testing. Unfortunately, I'd be very happy to talk more if you guys want, and just show you some results. So here is an input. The true label is French horn, and you can test for whatever concepts you want. Here, we just picked a set, doesn't matter from where. And then we are ordering them according to the rejection time. So this online testing procedure that we have has a rejection time. And in particular, the rejection time induces an order of importance. The sooner I reject, the more important this concept is in a very precise sense. And that's what you're seeing in the blue bars. In the blue line, what you see is the fraction of times that you reject. So the ones that are here are below alpha. So from this graph, what you should conclude is that all of the ones that are up there reject the null at level alpha. And the ones that don't, we are just going to call that they're unimportant. And in fact, this rejection, you can adjust it, as you can imagine, to have a control on the false discovery rate that I make in reporting these predictions. You can do things that perhaps are more interesting in settings where you actually know some notion of ground truth of concepts. So for example, this is a setting where experts have annotated ground truth labels of what distinguishes different types of birds. It's very complicated. It's a whole department on birds. Now, what we can now go is train these predictors, just take them off the shelf. These predictors never used these ground truth concepts. But then I can now go and question whether these concepts that the expert tell me are important for these predictions, whether they were captured by these models. And so here, what you see is that these 5 concepts reject our test. And so they are important. These concepts that, according to the experts, are not present in that type of bird, they indeed are not important for the predictor. Except this one. This one is present here, but it's not being used by the model that you train. And so now you really start getting to test for what are these concepts that these models have learned. You can do, as I said before, this global test over the distributions. You can find interesting things. For example, in this case, these are ImageNet examples. Here you have 2 dogs, right? And so the concept sibling is very important for this model, for example, because there happen to be 2 dogs. Or here, the concept fishing is also important because the dog seems to be fishing out a log. We actually have an online demo for this. We basically, you don't need to train any parametric model here. So everything is very fast. So this is a Hugging Face site where you can literally just upload whatever image you want. And this will run these tests in the background for whatever concepts you want to test. And it will tell you whether you reject or fail to reject a certain subset of test. This is my last slide. And just to tell you the following. You have so many language vision models now that maybe a reasonable metric that someone might want to construct on them is, have they learned similar concepts? So I'm not going to take you through the details of these tables, but this is just to say that now that you have a precise way of quantifying whether a concept is present or not, you can define a metric on that, and you can study how similar different language vision models are based on what concepts they've learned from the data. And so you can start, there's a lot of interesting sort of debugging and retraining ideas based on these kind of things. That's all I wanted to tell you. I think there are some very sort of interesting and fun problems at the intersection of trying to understand what these models do, but at the same time, making minimal assumptions about what these functions encode so that we can still say something about them. The first part on learn proximal networks is joint work with Xinghan Fang, who's a PhD student of mine, and Sam Buchanan, who's a TTIC. And the latter part on supervised learning, it's mostly done by Bipu Bharti and Jacopo Tenegi, who are PhD students, and my good friend Yaniv Romano from the Technion. And that's it. I'll be happy to take questions if there are any. Mm,
Going back to the first part, you mentioned you could draw samples from the learned. from
yes,
there.
that's right.
How's the compute time of that compared to the rather expensive compute time of drawing samples in the student model, and then how's the quality compare? Because of course, it's the sampling quality that is makes it.
Yeah. So invite me next year and I'll tell you. So we're working on this. So you as you know, you can construct diffusion processes based on scores. You can also construct diffusion processes based on proximal Langevin algorithms. Those have some very interesting properties. In some cases, the advantages can be made precise, and there are analytical precise advantages of using proximal stuff versus now whether that translates to practical advantages remains to be seen.
Also for the first project, so it's pretty cool to get to see this kind of the regression value. How does it work to get the reconstruction of the CT on a different view angle? I wonder, like, giving this kind of information that we can optimize to get the regression term, how do you think this can be helpful to further improve our target, for example, the reconstruction task? So for example, if you think, okay, we should adjust the regression in some kind of direction to further refine or
Yeah,
to
I see.
get the
I see.
for uncertainty, right? If you mentioned like about the sampling. So I just wonder, like, how do you think this can be helpful for our target task here?
So uncertainty you can directly quantify through this because it gets you an idea at least of these unnormalized densities.
Mhm.
So you could do some Bayesian uncertainty quantification that way. Now, optimizing that for the specific reconstruction task, sure. So what you could do, which we didn't, is use the information about the forward operator to sample, and then the samples would be perhaps better oriented to the conditional of that specific forward operator. It's kind of like doing unrolling with the forward operator that you care about. You could do that. We haven't done it, but I'm sure that if you do it, performance on that specific inverse problem will improve.
For the spatial local patch or region.
For example, whatever, let's say that you have a very specific deep learning task in mind, you could train this for that task and likely do better.
Thank you.
Also,
Yeah.
for second part, I showed like you have figure like showing an image along with lots of like concepts.
Yeah.
How do you get those concepts?
You can choose them. So you can choose them, and the only assumption is that these clip models or other vision language models have been trained to represent those concepts, which for a large family of concepts and models that seems to be true in practice.
So like in fact, how do you choose it? You choose like different like fix an image.
I fix the image and then you pick. So in the case of the cat, I choose to ask the concept cute and piano, and you can literally run these tests with those concepts.
Okay.
Yeah.
It seems the second part is related to Vinay's recent work, right? They use dictionary learning to interpret.
Yeah, I was wondering whether you can give a input and then decompose a concept.
You can.
Yeah.
You can, and people do that.
They use dictionary learning, right?
Yeah. Correct. But again, the reason people use dictionary learning in this setting is because you have a very large concept bank, and then and then once you have these very large concepts, then you might say, okay, let me find, surely a subset of these already span the concepts that I care about, and that's essentially a dictionary learning problem. Here, the problem is a bit different. Here, all I care about is, and I mean, you could do that, and then run these tests for the concepts that you found.
Yes.
Yeah. So it's complementary in some sense.
Okay.
Yeah.
All right.
Because we are running out of time. Let's
Yep.
Jerry again.
All right. Thank you.
Maybe I